The weather forecast you checked this morning, the climate model predicting the next decade of global warming, the nuclear simulation running inside a government laboratory, the financial risk calculation processed by a Wall Street bank, the trajectory calculation that guided a spacecraft past Jupiter. All of them, every single one, running on code written in a language that was invented before the microchip existed. 1957. Dwight Eisenhower is president. The Soviet Union has just launched Sputnik. Rock and roll is 3 years old. And at IBM's research laboratory on Madison Avenue in New York City, a team of 13 programmers led by a man named John Backus has just released the first version of a programming language they called FORTRAN, Formula Translation, a language designed to let scientists write mathematical equations in something that looked almost like real mathematics and have a machine understand it. Nobody expected it to last a decade. It has now lasted nearly 70 years, and it is not slowing down. FORTRAN is not a relic. It is not a museum piece. It is not something engineers use because they are too old or too stubborn to learn something new. It is running right now, today, on the fastest supercomputers ever built, solving problems that no other language can solve as fast. This is the story of how a programming language born in 1957 became immortal, and why the world would genuinely fall apart without it. To understand why FORTRAN was revolutionary, you need to understand what programming looked like before it. In the early 1950s, if you wanted to tell a computer to do something, you had to speak its language. Not a high-level language, the machine's actual language. Binary instructions, sequences of ones and zeros, or at best, assembly code, a thin layer of abbreviations that still required you to manage every register, every memory address, every single operation manually. Writing a program to solve a differential equation, the kind of calculations scientists and engineers needed constantly, took weeks, sometimes months. And when you were done, the program only ran on one specific machine. Move it to a different computer, and you start it over. John Backus joined IBM in 1950. He was a mathematician, not an engineer, and he found the process of programming a computer genuinely maddening. In his own words, he felt that programming was a black art, a private, arcane knowledge shared between a small priesthood of specialists. He wanted scientists to be able to write mathematics the way they thought about mathematics, not as machine instructions, as equations. So, in 1953, he wrote a memo to his manager proposing a project to develop a more practical mathematics language for the IBM 704. His manager approved it. He assembled a team, and over the next 4 years, they built something that had never existed before: a compiler. A compiler is a program that translates human-readable code into machine instructions automatically. Before FORTRAN, the idea that a machine could translate anything as complex as a mathematical formula was considered by most computer scientists to be impossible. Or at least they assumed any compiled code would be so inefficient compared to handwritten assembly that no serious programmer would use it. Backus and his team proved them wrong. The FORTRAN compiler, released in April 1957, produced machine code that was often as efficient as what expert programmers wrote by hand, sometimes better. The reaction from the scientific community was immediate. Physicists, chemists, engineers, aerodynamicists, people who had been held back from computation by the sheer difficulty of programming, suddenly had a tool they could actually use. FORTRAN spread through research laboratories like fire. Within 18 months of its release, more programs were being written in FORTRAN than in any other language. The priesthood was over. Science could finally compute. Here is the question that everyone asks. Python exists, C++ exists, Julia exists. Why in 2026 would anyone still choose to write in a language from 1957? The answer is one word: speed. Not just fast. faster than almost everything else that exists. And in the world of scientific computing, speed is not a luxury. It is the difference between a weather forecast delivered in time to evacuate a city and one that arrives 3 hours after the storm. Fortran was designed from its very first line of code to do one thing exceptionally well: number crunching. Specifically, operations on arrays, grids of numbers that represent the physical world, temperature readings across a continent, air pressure at every altitude, the position of every particle in a fluid dynamics simulation. Modern Fortran, and it is modern, the current standard is Fortran 2023, handles arrays as native, first-class objects. In most other languages, working with large arrays requires libraries, overhead, translation layers. In Fortran, the language itself understands arrays at a fundamental level. The compiler can optimize array operations in ways that other compilers simply cannot. There's also something called memory locality. When a processor wants to calculate something, it needs the data it's working on to be close to hand, in its fast cache memory rather than being fetched from slower RAM. Fortran's memory model, the way it stores arrays in memory, is designed to maximize this. The data the processor needs is almost always exactly where it expects it to be. The result, on the kinds of calculations that run weather models, climate simulations, and nuclear physics codes, Fortran is routinely 10 to 30% faster than equivalent C++ code, on some operations, more. For a weather model that takes 12 hours to run on a supercomputer, a 30% performance improvement means it runs in about 8.5 hours instead. That's 3.5 extra hours of forecast lead time, 3.5 extra hours to warn people. Speed in scientific computing is not abstract. Speed saves lives. But speed alone does not explain why Fortran refuses to die. Because if speed were the only consideration, every scientific institution could rebuild their codebase from scratch in a modern language optimized for performance. They won't, and the reason why is the most fascinating and terrifying aspect of the entire story. Over the past 68 years, the world's scientific institutions have written an almost incomprehensible amount of Fortran code. The National Center for Atmospheric Research has weather and climate models with individual codebases exceeding 1 million lines of Fortran. The European Center for Medium-Range Weather Forecasts, ECMWF, which produces what many consider the world's best weather forecast, runs on a Fortran codebase that has been continuously developed since the 1970s. These codebases are not just large, they are validated. Every line has been tested against the real world for decades. Every algorithm has been checked, rechecked, published, peer-reviewed, and verified against physical observation. The code is, in the most literal sense, proven to be correct. Rewriting any of these systems in another language would take years. It would cost billions. And the terrifying part, the part that keeps the scientists who run these models awake at night, is that when you rewrite a complex numerical system, you introduce errors. Subtle numerical errors, tiny differences in floating point precision, in the order of operations, in how memory is handled. Errors that might not show up in testing. Errors that might only emerge years later when the model quietly begins predicting the wrong thing. One professor described it this way: every science lab has at least one Fortran codebase they cannot kill. It's like a family heirloom. Nobody knows exactly who wrote it, but everyone is afraid to delete it. So the code stays. And because the code stays, new scientists learn to maintain it. And because new scientists learn to maintain it, they sometimes add new features in Fortran, because that is the language the codebase is written in. The legacy does not just persist, it grows. Let me make this specific because I want you to understand that this is not abstract. History, Fortran is actively running the world right now, today, in ways that affect your daily life. Every morning, the European Center for Medium-Range Weather Forecasts runs its integrated forecasting system. It processes data from thousands of weather stations, satellites, ocean buoys, and weather balloons. It runs a physics simulation of the entire atmosphere of the Earth. It produces the forecast you check on your phone. It runs in FORTRAN. The National Oceanic and Atmospheric Administration, NOAA, runs the global forecasting system, which powers most American weather apps. FORTRAN. The UK Met Office, which provides weather forecasts for aviation, shipping, and national emergency planning across Britain and beyond, runs the Unified model, a climate and weather simulation system with over 1 million lines of FORTRAN code that has been continuously developed since 1991. But weather is only the beginning. The United States Department of Energy's national laboratories, Los Alamos, Lawrence Livermore, Sandia, run nuclear weapons simulations on the world's most powerful supercomputers. These are the codes that verify whether America's nuclear deterrent still works. NASA uses FORTRAN for aerodynamics simulations, orbital mechanics calculations, and climate modeling. The legacy stretches back to the Apollo program. The code that helped put humans on the moon was FORTRAN. Some of those routines, refined and updated, are still in use today. Every programming language that came after FORTRAN owes it a debt. The concept of the compiler, the idea of writing code in human-readable syntax, the notion that a machine should translate your intentions rather than requiring you to specify every mechanical step. These are FORTRAN's gifts to the entire field of computing. The language that was supposed to be temporary, the tool that was meant to last a few years until something better came along, the relic that everyone has been predicting the death of for 60 years. It is still running, right now, on the machine that told you whether to bring an umbrella today. And it will probably still be running when your grandchildren check the forecast.